Hello everyone, this is Balu. Welcome to my channel Steel Cave. In this video, I am going to discuss about shear strength of plate girder. In the previous videos, I have discussed about the introduction part and also the behavior of the plate girder. If you have not yet watched those videos, please go through that videos. And also, I am providing the links for those videos in the description. And also, this video is related to the series of videos regarding the design of the plate girder. And also, each and every video is interlinked. If you watch those old videos only, then you can get the clear-cut understanding regarding the plate girder. So please watch those old videos, and also if you have not yet subscribed my channel, please subscribe my channel and also share with your friends who are pursuing civil engineering degree or also who are working in the civil engineering industry. Okay, let me quickly summarize the behavior of the plate girder which I have discussed in the old video. So whenever the load which is going to act on the plate girder, so consider, let us say P. Here you can see this is a plate girder which is having the transverse stiffness, and also T is the thickness of the web, and also D is the depth of the web. So whenever the load acts on the plate girder at high shear concentration region, that may be at the supports or maybe at the concentrated loads, there are principal planes present near the high shear concentrated regions. In those principal planes, actually those principal planes are inclined to the axis of the plate girder. In those principal planes, there are two principal stresses in the plate girder. That is, one is the diagonal compression and one is the diagonal tension. So diagonal tension is going to be resisted by the web itself. And coming to the diagonal compression, to arrest this diagonal compression, we have to provide the transverse stiffeners or maybe the longitudinal stiffeners also, so that the panel is going to act as a unit and there will be the tension field action is going to be generated in the plate girder. So this diagonal compression component is going to be transferred to the flange and also to the stiffener. And coming to the strength of the plate girder, the strength of the plate girder is the sum of the strength before onset buckling of the web and also the strength after post buckling of the web. That means whenever the load is going to act on the plate girder, initially the web is going to undergo buckling, and after the buckling there is a tension field action is going to be generated in the plate girder. So we can say the strength of the plate girder is the sum of the strength which is going to be generated before buckling of the web and also the post buckling strength which is going to be generated due to the tension field action of the plate girder. So once the buckling is going to be initiated in the web, then after that this plate girder is going to behave like a end truss. Then what is the behavior of this end truss is, whenever the load is going to act on this end truss, the compression is going to be resisted by the vertical members and also tension is going to be resisted by the inclined members. We can say these are the bracings, you can say. So in the similar fashion to the end truss, the plate girder is going to be behave. So the compression is going to be resisted by the whatever the stiffeners, and also the tension is going to be resisted by the web itself. So this is the behavior of the plate girder. I have already discussed in the old video, but let me give the summary on the whatever the behavior of the plate girder so you can understand the better regarding the shear strength of the plate girder. So let's get into the shear strength of the plate girder. The shear strength depends on the whatever the spacing between the transverse stiffeners, that is C, and also D by T ratio of the web. Here you can see D is the depth of the web and also T is the thickness of the web. C comma D by 2 are the governing factors which are going to influence the shear strength of the plate girder, and providing this transverse stiffeners is going to increase the ultimate shear strength of the web. And coming to the shear capacity of the web, it is the sum of the strength before onset of buckling and also the strength after post buckling of the web. I already discussed regarding this whatever the onset buckling and also post buckling. Initially the web is going to buckle, and after that the strength is going to be generated due to the tension field action, and this tension field action is due to the whatever the panel strength. That is, after providing this transverse stiffness, this whatever this panel is going to act as a unit, and in this unit tension field action is going to be generated. And due to the application of the external load, the shear load is going to act on this panel. As the shear load is going to be increased due to the application of the external load, the web starts buckling. And also the load can be still increased and additional reserve strength is gained by the tension field action. So I already explained clearly the strength is due to the initial buckling strength and also the strength which is generated after the buckling, which is nothing but the tension field action strength. Once the tension field comes into the picture, the girder acts like a end truss. Here you can see, if I consider this panel, because of this external load, the shear stress or shear load is going to act on this panel. And because of this shear load on this panel, you can see this part of the panel is going to buckle. And this is nothing but the buckling panel. And the tension is going to act in this, whatever the panel, which is nothing but tension panel. So you can see, this is the shear stress which is going to generated on all the four sides of the panel of the plate girder. For example, if you are going to increase the spacing in between the transverse stiffeners, then what will going to happen? Whatever the tension field action, it is not going to develop whatever the efficiently. So that the strength of the plate girder, that is the shear strength of the plate girder, is going to decrease gradually as the spacing between the transverse stiffeners is going to increase. So here you can see this is the buckled panel. Once the initial buckling is going to be generated in the web, and you can see this is the buckled panel of the plate girder. This is how the web is going to buckle. Now here you can see this is the tau CRE is the whatever the shear stress which is going to be generated in the panel web. Tau CRE is nothing but the elastic critical shear stress, and this is the maximum compressible stress which is going to be resisted by the web panel before buckling. So after this stress is going to be achieved in the whatever the plate girder, the buckling is going to be started in the web. So we are going to design whatever the web for this whatever the elastic critical stress, and after the elastic critical stress is going to be reached, then after that buckling is going to be initiated, and the whatever the further strength is going to be generated by the tension field action. The engineer is going to design for the elastic critical shear stress. So once the elastic critical shear stress is going to be reached, the web starts buckling. So the further strength is going to be generated by the tension field action. So if you want the strength of the tension field action, then you can design for the tension field actions. So if you are looking just for the initial buckling only, then you can design the plate girder for the initial buckling, that is elastic critical shear stress only. So the concept is, if you want the web to resist the load which is under the elastic critical shear stress only, then you can check for the elastic critical shear stress and you can leave the design. But if you want to design for the tension field action, then in this case, the web is going to buckle initially and it will reach the elastic critical shear stress, and the further strength is gained by the tension field action. So when we have to check for the shear buckling, then you have these two conditions. Shear buckling can be checked whenever the depth to thickness of the web ratio is greater than 67 epsilon. Epsilon is, you all know that is 250 by Fy, that is the grade of the steel. For the unstiffened web, shear buckling shall be verified whenever the depth to thickness of web is greater than 67 epsilon. And for the stiffened web, means when we are going to provide the transverse stiffness or longitudinal stiffness, then it is called a stiffened web. And if you are not going to provide any stiffness, then it is nothing but the unstiffened web. So shear buckling can be verified whenever it exceeds these limits. Now coming to the elastic critical shear stress formula, this is the formula which is going to govern the elastic critical shear stress. Once the elastic critical shear stress is going to be reached, the web starts buckling and the further strength is going to be gained by the tension field action. Kv is a parameter which is going to depends on the C, that is the spacing between the transverse stiffness and also depth to thickness ratio. And E is the modulus of elasticity, TW is the thickness of the web, D is the depth of the web, mu is the Poisson's ratio. So this is regarding the shear strength of the plate girder. So shear strength is going to be generated due to the web. So before initiation of the buckling, the strength in the web is nothing but the elastic critical shear stress. Once the elastic critical shear stress is going to be reached, the web starts buckling, and after the further strength is due to the tension field action. So this is nothing but the shear strength of the plate girder. If you like my video, please like the video and also share with your friends if you like my content. Thank you.